Hello again, this is Professor Shannon Gracey from Maricosta College in not so sunny San Diego today. And we'll be covering how to evaluate limits analytically. So you can go ahead and read the goals, the outcomes for this section, and they're up there. We are working out of the Larson and Edwards Calculus text. Which is what this guided notebook is based on. If you're not in one of my classes, feel free to go to www.mathchick.net to download the guided notebook for free if you'd like to and learn calculus along with us. All right, so go ahead and pause the movie and warm it on up. So now, we've got, it is important, we're going to be utilizing our algebra skills. Remember, starts with A, not a bad word, and we're basically going to be rewriting equivalent expressions. This is not an equation, it is an expression, a rational expression. And so what we have here, just in case you forgot, is we have 2x, the quantity cubed, minus 3 cubed, all over 2x minus 3, and this in turn factors, the numerator factors as 2x minus 3 times 2x squared plus 2x times 3 plus 3 squared, and that's all over 2x minus 3. If you need to look up the formula I used, it is the difference of squares factoring formula. And again, if you need some extra help with that, you can go ahead and go on to my, let's see, it'd be the introductory algebra course, and chapter 6 deals with factoring skills and strategies. Okay, so here we go. You see we have a common factor of 2x minus 3, so that divides out, and we'll end up with 4x squared plus 6x plus 9, and we're done. How'd you guys do? Awesome. All right, so next up, so I'll just write what strategy we used. This was difference of 2 cubes. Okay, now here the strategy that you probably used was great, factoring by grouping. So factoring by grouping, you basically will have, typically it's 4 terms. Sometimes you got to do a little bit more magic on it to make it happen with some of the harder ones. But here we've got two sets of 2 terms that we can look at. So if you just kind of look at the blue group first of all, actually let me do that in a different color since I write in blue. All right, so this will be black. So basically this is equivalent to, what can I factor out of the black group, the 2 terms I underlined in black? Great, an x squared, and then we're left with x minus 2. All right, so now what do I need to add or subtract to factor the green group so that I'll get an x minus 2 factored out? Or I'll get a binomial factor of x minus 2. Good. If I do a minus 4, then I'll be left with x minus 2. Perfect. So now what I've got going on is I've taken this from 4 terms to 2 terms, right? And now I'm going to get this into 1 term where everything's being multiplied. That's factored form. So if you see, we've got a common binomial factor of x minus 2, so we'll be factoring that guy out. And when we do so, we'll have our x minus 2. And then we'll be left with x squared minus 4. But be careful, because x squared minus 4 itself is what? Good. It's a, let's see, I'm running out of colors here. This is a difference of two squares. So, factoring further, we'll have x minus 2 times, good, we'll have x minus 2 times x plus 2, and so this is equivalent, this here is equivalent to this. And then we're all done. All right? Doing okay? Awesome. All right, so now, one reason why we put in a factoring by grouping problem there is because you can use that skill to factor a trinomial. Okay, so here we go. What we're going to do, the way you can use trial and error, that's totally fine. I'm going to show you how to do it using factoring by grouping. So basically, you know, on the side somewhere, you make an X or a box. You've probably learned this at some point in your math life. And we're looking at things that are in the form of, you know, ax squared plus bx plus c. And so what goes here is a times c. And our a is 3 and our c is negative 4. So we're going to be putting in negative 12. All right? And then what goes down here is our b, which is negative 11. And then what we need to figure out is what, you know, two numbers that will have a negative product, negative 12, and when you combine like terms, you end up getting negative 11. So what two numbers work? Awesome. Negative 12 and positive 1. So then all we do here is we rewrite this trinomial as an expression with 4 terms instead of 3, keeping the very first one and the very last one the same. And what we do is we rewrite negative 11x using what we found in our x here. Okay, so far? All right. So then this will be equivalent to, so now using our factoring by grouping skills, we've got this guy here and we've got this guy here. So factoring out a 3x, we'll be left with, good, x minus 4. And then over here, factoring out a positive 1, we'll be left with our x minus 4. So that's the result of the black group and then the green group, all right? And continuing, we now have our binomial common factor of x minus 4. So then when we factor that guy out, we're left with, great, 3x plus 1. So all we had to do was factor out this guy, and then we're left with the 3x plus 1. All right? And guess what? Woo, we're all done. Okay. Oops. Here we go. All right. Feeling pretty warmed up? Now we're going to go to a skill where you may or may not have used this very much when you were in college algebra or pre-calculus, you know. Basically, we're going to run into some situations where we will need to rationalize a numerator. So you're more used to rationalizing denominators, but that's okay. We'll go ahead and we'll rationalize the numerator, and you'll see why. There's a whole evil plan, okay? So to rationalize the numerator, basically you are looking to generate a difference of squares situation. So here you've got something minus 2, so you want to multiply it by that something plus 2. So what's that something? Very good, the square root of x plus 1. And the reason we're doing this is because this is going to generate a difference of squares situation where we won't have a middle term and we'll have gotten rid of the radical that's in the numerator. So now you've got to balance it out by multiplying the denominator by that same quantity. And then continuing with our algebra, what will happen is we'll get the square root of x plus 1 squared minus 2 squared over x minus 3, and then don't bother multiplying this out. That's the trick here. That's not something that my leftiness is getting in the way a little. That's not something that's going to help us. So the trick is leave that denominator where it's not, leave the denominator where it is not expanded out. Okay, so what happens when I square a square root? Good. I just get what's inside the radical, and then I'll have minus 4 all over x minus 3 times root x plus 1 plus 2. And then look what happens. Do you see I get an x minus 3 in the numerator, which will be super awesome because then I'll be able to divide out this x minus 3. And dividing this out, we get, at the end of the day, we get 1 over root x plus 1 plus 2. So this is a valuable skill for evaluating limits analytically when you get an indeterminate result when you use something called direct substitution. We talked a little bit about indeterminate results. Indeterminate means you get 0 over 0, all right, as you're evaluating a limit. So we'll get more into that as we go. All right, so just to make sure you're okay with some of these equivalences, you know, this product is this right here, all right? And then I think the rest of them you'll probably be good to go. Okay, so here we go. Let's go ahead and some more practice stuff that will be useful to us. We'll be kind of practicing again the difference between function values and limits. All right. So if if f at x is negative 2, right? What is f at 4? Now remember, it's so easy, it's hard. Good, you got it. F at 4 is just going to be negative 2, right? So basically what happens is if we take a picture of that graph, right? I don't know, do we want to use technology? What do I have here? If we take, if we do to, what was it? Negative 2, right? And we graph. So this is, and let me just zoom standard. Okay, so let's get a screenshot of this guy. New. Copy. Okay, so if you look here, you know, this is a standard scale here. So it's you know, this is our f at x here. This is our x, and we go from, you know, this is 10, 10, negative 10, negative 10, right? And this here, you know, is our line. F at x is equal to negative 2. So here, what we found was for f of 4, which is what we were evaluating, 1, 2, 3, 4, we're down here still, right? So this here is negative 2, which is also f at 4 equals negative 2, right? So thinking about our lesson from the last time, what is the limit as x approaches 4 of f of x, which is negative 2? Remember, the result of a limit is a y value. So what do we get for the answer? Good. Oops. Yeah, there we go. So we just get negative 2, right? So what do we notice here? We notice that the result of the limit is a y value, and it happens to be the same y value as the function value, right? So it turns out, and let me see if I have it written below. Oh, okay. So here we can go ahead and we can, actually I'll do the rest of them step by step, but we can go ahead and answer this question here. I'm just going to say equals negative 2, and then we'll say C above. I'm ahead of myself, guys. All right, so next up, if we have f at x is equal to x, what is f at 4 going to be? Perfect. You just plug in 4 wherever you see an x, so you're just going to get 4, right? And then why don't we go ahead and do that limit stuff down here? Let's find the limit with our calculator, graphing calculator, and make a picture. So now we'll change our graph to, just clear this one out and be up here. We'll change our graph to f of x is x. Okay, so now again we're at this is our f of x. This is x, and then we go from negative 10 to 10 on both the axes. So remember, our limit, the output of a limit is a y value. Perfect. So here, when I go to x is 4, I go 1, 2, 3, 4, and then you just go up and you go, that's where you bump the graph. And you see that this here is L, right, which is equal to good 4, but that in turn is equal to f at 4. You see how they're connecting here? All right, and I'm kind of prepping you for ideas about continuity, all right? So here, at the end of the day, we have this ordered pair, which was at 4, 4. And so the result of this limit is 4. Perfect. And again, as you notice, as you're approaching 4, x is 4 from the left side, you get an output of 4. As you approach x is 4 from the right side, you get x is 4. So that is why the limit is 4 for this part. Alrighty, so now coming back, we're going to have f of x is x cubed this time. So we'll go to our y equals. We'll clear this. I'll do a different color. And this will be x cubed graph. Oh, and actually, we're going to need to change our scale, right? Because we're still approaching 4. So let's change our window to the, the x's can be, let's go just negative 5 to 5. And then the y's are going to have to be higher, aren't they? So y minimum, let's just do let's just do like negative 100 to 100 or something like that. And then we can adjust the scale on the y to 10. And let's check that out. There we go. So now, let's just go ahead and do, we'll go to second, calculate value, and we'll hit in x is 4. And so you'll get that ordered pair on the graph. So we'll copy this one. Okay, so now you can see that, so this here is the ordered pair 4, 64, right? And so here we're at, if you go across, you know, y equals 64 is going to be straight across from there. So that would be what, 10, 20, 30, 40, 50, 64 would be probably just under. I'm trying to get my line straight for you. Okay, so far. So this again is our L, which happens to be 64, which happens to also be f at 4 for this function, right? So here, our limit, as you see, as you approach, if you look at the graph, as you trace along and you're approaching x is 4 from the left side, you get an output of 64. And from the right side, as you approach x is 4, you get an output of 64. So the answer is, good, 64. All right, so now let's go ahead and before we talk about direct substitution, okay, let's talk about some basic limits. We actually just learned these. So the first one is basically if you're evaluating the limit of a horizontal line, you're just going to get the output, the y value, b. Okay, and over here, as you approach an x value on the graph, y equals x, or f of x equals x, you're just going to get the same y value as the value you're approaching. So you'll get c. And then over here, if you raise x to a power, right, as x is approaching c, it's just going to be c raised to that power, right? So this is an example of that. The n in this case was 3, and the c we were approaching was 4. Okay, so this corresponds to the limit as x approaches c of x cubed equals c cubed, which actually I'm going to put n so you have the general formula next to it. And then this one was the limit as x approaches c of x is just going to be c. And then up here, this was that horizontal line. So the limit as x approaches c of this constant b is just going to be b. Groovy? Okay, so now coming over here, it turns out that you should always use something called direct substitution first to see if it works, all right? And so basically, if your limit of your function value as x approaches c is the same as f at c, then you can use direct substitution. So here, in the problems before that we were doing, do you see that if we had named, let's try it here first, if f of x was equal to x, and we found, remember before we found f of 4 was 4, do you see that that function value is the same? It's the same as that limit, right? And so this is a result of, this here is a result of you could also do it as a result of direct substitution. Okay, which we're going to refer to, you know, as DS for direct substitution. Gotcha? All right. So now this guy, the limit as x approaches 4 of x cubed, using direct substitution, we could say, okay, let's try it. I would have 4 cubed, right? And so what you do is you take the number you're approaching and you plug it in here, right? And then what do we get at the end of the day? We got the fact that the limit as x approaches 4 of x cubed is equal to 64. 64 is a perfectly lovely number, no problems with it, so you're all done. So this is a result of direct substitution. And the cool thing is you already know how to do that. You've been evaluating functions at specific x values forever, right? So this is something that it looks a little different at first, but you're used to doing this. You can do it, all right? Okay. Okay, so that was our direct substitution. So now we've got some theorem here, properties of limits, right? So basically, if you have a scalar multiple, right, the limit as x approaches some domain value of a constant times your function, you're just going to get the constant times whatever the resulting limit would have been, all right? And sum or difference of the limit of a sum or difference of functions is the sum or difference of the limits, right? And continuing, okay, we're going, you know, the limit of a product is the product of the limits. The limit of a quotient is the quotient of the limits, as long as the limit of the expression in the denominator does not equal 0. And then the power rule for limits is if you have a function of x raised to a power and you're taking that limit, then it's that limit raised to the power. Okay? So here we go. We're just going to do a couple of these. By the way, on an exam, you know, we wouldn't be breaking it down like this. This is just to teach you. All right? So here we go. What do you think? Of these up here, right? Which number do you think you're using? We could let f of x be 5, right? And g of x could be x, or negative x if you want. The way I've set it up, we're going to have, we're going to have the sum of the limit of a sum of functions, right? And that's number, what? 2, sum or difference property. Okay, so, okay, let's check it out. This is, you know, how one would break it down. This is equivalent to the limit as x approaches 2 of 5 minus the limit as x approaches 2 of x. And didn't this break down to those basic limits? Good. So we'll end up with, what do we get out here? The limit of a constant is the constant. Perfect. And then, awesome. Using direct substitution, right? We directly substitute x equal 2 into the x, which will just give us 2. So let's match those up. So the output of this limit here is 5. The output of this limit here is 2. So now we simply take the difference of between 5 and 2 and we get 3. So the result of this limit is 3. Good so far? Awesome. All right. Now, what about this guy? There's a bit going on here, right? We've got, first of all, good, a quotient, right? So we've got the, I'll just put the numbers. There's a lot going on here. So we've got a quotient, which is number 4, right? So let's work with that one at first. So this would be equal to the limit as x approaches 0 of, actually, of 6x minus 5, that quantity, divided by the limit as x approaches 0 of x cubed minus 2. So this was the property number 4. Now, again, we've got a couple of differences, right? But we're not going to break it down. You know what we're going to do this time? We're going to go ahead and use direct substitution. If a person were to break this one down, do you see that we would be using scalar multiple with the 6 times x, difference of functions with each of those expressions, and then a function raised to a power, right? So I think we're actually using everything except for number 3. So, did I say that right? Yes, everything except for number 3. So, we'll have number 4. We'd have number 2. That's the difference of functions. And then we would have number 1, and we would have number 5. Okay? But in this case, we're going to just break down the f of x and g of x as f of x is that numerator, 6x minus 5, and g of x is that denominator, x cubed minus 2. So, here we go. Using direct sub, let me make my room here. Using direct substitution, right, we're going to use direct sub in both of them, okay? So we're going to have 6 times, good, 0 minus 5 over 0 cubed minus 2. So what we did is x was approaching 0, so we plugged in 0 wherever there was an x. Same here. And now we will get 0 minus 5 is negative 5. 0 minus 2 is negative 2. So at the end of the day, our result of this limit is 5/2. Okay? So we basically wrote equivalence relationships the whole way until we got to our result of 5/2. Sorry, this 5's a little wild. Okay, so now, here we go. As you may have noticed, there's, some special cases. Limits of polynomial and rational functions. Basically, you evaluate the polynomial or the rational at the domain value you're approaching, C. And as long as C is in the domain, right, you will have, you will be able to just evaluate the limit using direct substitution. So, same with the rational. So let's check them out. I mean, a lot of times this is one of those things that it's just become so second nature. So using direct substitution, right, we have, this is going to equal to, good, negative 3 to the 4th. So I'm just putting in, wherever I see an x, I'm putting in a 3, plus 6 times 3 squared minus 2. So we've got x is here, x is approaching 3, and that's where we plugged it in. And now, at the end of the day, well, almost at the end of the day, we'll get negative 81 plus 54 minus 2. And what's that going to give us? 11, minus 4 is 7. 7 minus 5 is 2. So negative 27 minus 2. I believe we get negative 29. Does that look okay to you guys? Let's see if I made up my own math. I think I'm getting a little bit of a cold coming on. Nope, we're good. All right. How's it going? Awesome. All right, so now here we go. Same with this one. Try it out first using direct substitution. Notice that the only time I can take my limit notation out is once I have directly substitute values, okay? So here we'll get, perfect, negative 4, the quantity cubed, minus 1 over 2 times negative 4 plus 7. So wherever I saw an x, I plugged in negative 4 because that's the domain value we're approaching. So what happened was I get negative 64 minus 1 over negative 8 plus 7, which is negative 65 over negative 1, which gives us positive 65. Good so far? Awesome! Okay, same with the limit of a radical, okay? As long as you're approaching a value that is in the domain of the radical, you're good to go. Just evaluate the expression that's in the limit at that number. So here we go, using direct substitution again. We will have the square root of 225 and what is that? Beautiful, 15. Okay, you guys try this next one. Okay, so again, using direct substitution, we get the fifth root of negative 243, right? So the index on that is 5. This is how we matched it up. And we will get, now what number raised to the 5th power is equal to negative 243? Good, we would have the 5th root of negative 3 to the 5th, which is just going to give us negative 3. Awesome. So this is our equivalence. Forgot to plug that in or highlight that. Okay, so now the limit of a composite function. So like I had told you guys, you know, we are going to be decomposing compositions, you know, and stuff like that. So this is something that we end up using all the time, but we forget we're using it. Okay, so just kind of go with me on this. All right, so here we go. So basically, let's try to keep this up for the following. So we've got this composite function. H of x is equal to f evaluated at g of x. Well, this composite is specifically sine squared at x. So what is sine squared at x? So if I have, so we've said that h of x is sine squared at x. Could I rewrite that? Good. It's sine at x multiplied to itself twice, right? Which is denoted like that. So f of x is what? What's the most outside thing going on? Perfect. You've got something being squared. And g of x is that something. Awesome. So now our c from the example is pi over 4. So if you're tying this to the theorem, right, the c is going to end up being pi over 4, all right? So now, oh, I answered the question. I should stop doing that, right? So what is g at pi over 4? Good. It's the sine function evaluated at pi over 4, which is Good, root 2 over 2, or 1 over root 2 if you don't rationalize. So we just plugged in pi over 4, right, wherever we saw an x, and that's what we got out. So now let's think about what we're doing, all right? So if we're looking here and we're breaking this down a bit, okay? So so here what we'll have is we could say that the limit as x approaches pi over 2 of blah, 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 blah. Okay, so now we could say that the limit, so that's kind of the first one here. What did we do? We sort of said, okay, the limit as x approaches pi over 4 of sine at x is equal to root 2 over 2. Would you agree that that's equivalent? Awesome. All right. So this is like that very first part right here. Now, if we go to that next step, right? As we approach the limit that we got of our function. So as we approach root 2 over 2 of f of x, which we described as being x squared, then what would that give us? That would give us root 2 over 2, the quantity squared, which at the end of the day is what? 2/4, which is 1/2. Good so far? So now we're basically taking the result of that first one, right? So I'll do a different color. We basically are approaching the result, the limit L, right? And our function f, we're going to be plugging that in to that function. So that's what we got out, all right? So identifying this here is the L that we got from the first one. Now, putting it all together, what we really figured out was, as we approach x over 4 of sine squared at x, this limit, it's equivalent to this. So at the end of the day, we get 1/2. Now don't freak out about that. It might be even more illuminating to write it as, okay, the limit as x approaches pi over 4 of sine at x squared is equivalent to the limit as x approaches pi over 4 of sine at x, this whole quantity squared. Good so far? Right. So what we're saying is that that limit can go inside or outside the composition. All right? Okay. So trig functions, same deal. As long as you're approaching a value that's within a domain of a trig function, you're good to go, right? So what we've got going on now is the problem here with trig functions is this. Many times people are a little trepidatious about trig, first of all. So get over it. You'll be better at it at the end of the semester. And then secondly, you really have to know the domain restrictions. Basically, review your trig stuff. We can talk about things as we go on during the course, but I can't totally reteach you trig. All right. So just do your best. You'll catch on again. At the end, you'll start remembering stuff. And I will show you how I think about these things. I never memorize the tangent, the outputs of the tangent function or anything except for the cosine and sine functions. So basically, this is equivalent to the limit as x approaches 2 pi over 3 of sine at x over cosine at x using our quotient identity for tangent at x. So now I'm really good with the sine and cosine outputs. So basically what I'm doing here is this is equivalent to sine at 2 pi over 3 over cosine at 2 pi over 3, which is what? What quadrant is that in? Beautiful, quadrant 2. And by the way, over here, do you see I did not directly substitute because I wanted to show you a different way of thinking about it, but then at the next equal sign I directly substituted. So I was able to lose that limit notation. So I basically went here, x is approaching 2 pi's over 3, and that's where I plugged them in. So now, continuing, what we're going to have is sine at 2 pi over 3 is going to be positive. Now what's going on is we're going to sine at 2 pi over 3, like we said, is in quadrant 2. We're going to get root 3 over 2 over, perfect, negative 1/2. This here is the output of the whole sine function, and this guy here is the output of the cosine function at that value. At the end of the day, we're going to end up with, negative root 3. And we're all done. Groovy? Awesome. Whoops. Alrighty. So now over here, what are we doing? Good. We've got, by direct substitution, cosine at pi. So wherever we saw an x, we put a pi. And the end result of that is beautiful, negative 1. All right, again, this is considered, the cosecant function is considered a reciprocal function. So I'm going to say this is equivalent to the limit as x approaches pi of 1 over sine at x over 6. That's using our reciprocal identity for the cosecant function. Right? And now plugging in, I'll have the limit. Oops, sorry, I don't need my limit anymore because I'm now directly substituting. So that's what we did up here immediately. Now we'll do it here for this problem. So this will end up being 1 over sine at pi over 6. So wherever I saw an x, I plugged in pi. And evaluating, we'll have 1 over 1/2, because that is the value of the sine function at pi over 6. And finally, that gives us a result of 2. Doing okay so far? Awesome. You know, I know that some of these videos get long. I just like doing the whole lecture at once. Remember, you can pause it, take note of, you know, what time you're on, and then just go right back to that part of the video and finish watching it later. All right, so now here's where we get to kind of the meat and potatoes of limit stuff, or I guess tofu and potatoes if you're vegetarian. So what'll happen is we've worked on this one actually quite a bit with our problem that we worked on at first in our last lecture, 1.2. So here, if you recall, when we use direct substitution here, what's going to happen? Right? We're going to end up with -1, the quantity cubed, plus 1 over negative 1 plus 1. So, hey, did what we're supposed to, following all the rules here. But unfortunately, it sucks because you get one of those weird things out, right? You get 0 over 0. This is considered to be indeterminate. Which means in the format it's currently in, we can't determine the limit. In the format the expression is currently in, we cannot determine the limit. But what's that word? Starts with an A, not a bad word. You got it, algebra. Remember, we can use algebra to rewrite this expression so that we can consider a function that agrees with the original at all but one point, right? That single excluded domain value. Because remember that a function value does not need to be existing on the graph. So the function does not have to exist at that input value for a limit to exist, right? So here, the limit as x approaches negative 1 of x cubed plus 1 over x plus 1, remember, is going to be equivalent to the limit as x approaches negative 1. And we had factored before, and we got, let me kind of block this guy off, and we had gotten what? Good. We got x plus 1 times x squared minus x plus 1 all over x plus 1. The x plus 1's divide out to be 1. So then now we can use, now we get the limit as x approaches negative 1 of this x squared minus x plus 1, right? We're dealing with the limit. We're not rewriting the function. So basically, we don't have to worry about the excluded value of negative 1. So plug in this guy in using direct substitution on this equivalent expression, except at one point. What's going to happen? We're going to get negative 1, the quantity squared, minus negative 1 plus 1. And what happened with that boy, that bad boy? We'll get 1 plus 1 plus 1. So I'll come up here a little. Which is 3. And as you recall on that one problem, that's the limit that we got graphically. Basically, to make a long story short, if you get a result of 0 over 0, it means more work. All right? So again, I'm going to make you chant like a weird math cult. We're going to say 0 over 0 means more work 5 times. Ready? 0 over 0 means more work. 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 And come on with me. 0 over 0 means more work. Right? So it is good to find out that it didn't work out. All right? But a lot of times people stop there. And, you know, that's kind of like washing your hair but not rinsing out the soap. That would suck, wouldn't it? So here, what we've got to do is once we find out we got a result of 0 over 0, that's like how we washed our hair. And then doing the algebra and completing the problem, or using trig identities and completing the problem, basically enables us to rinse the soap out of our hair. All right? Okay, so this guy, if we plug in using direct substitution, right? If we plug in 3, let's see what we get. We'll get 3 squared minus 5 times 3 plus 6 over 3 minus 3. So when we used our direct sub, I'm sure you can see we already have kind of a problem child showing up. Do you see that that's going to be equal to? Good. 0 over 0, which means more work. And in this case, the more work means algebra, right? Because if you have a rational expression, you can simplify it often. So let's go ahead and factor. Now, while we're working on this, we need to keep our limit notation. When can you take that limit notation off? Beautiful, when you apply a direct substitution. So this guy factors as, great, x minus 2 times x minus 3 over x minus 3. So you'll see that these guys here divide out, the problem children divide out, and we end up with the limit as x approaches 3 of x minus 2, right? And then now using direct substitution, what do we get? Beautiful. We can take that limit notation off, and we just get 3 minus 2, which is 1. We just plugged in a 3 where there was an x and got a result of 1. Good so far? All righty. So now we get to something called the squeeze theorem. The squeeze theorem. So the squeeze theorem basically says, hey, let's say that you don't know the limit of this function, right, f. But suppose that you know the limits of two functions which are right next to it at that input value, right, and they're the same. So basically what happens is the limit for f of x as x approaches c has to be the same as those other limits because it's being squeezed in there at that input value. I like to use this guy here to illustrate that theorem. This is how it works, and you'll need to remember a couple of things as we go through this guy. One of the tools that we'll be using is, of course, the area of a triangle is equal to, good, half times base times height. We'll be using the area of a sector is equal to, do you guys remember that one? Good, 1/2 theta times r squared. Now, theta has to be in radians, all right, so be careful with that. And let's see. Oh, we'll also be using this idea later. If if A is less than or equal to C, which is less than or equal to B, then 1 over A is greater than or equal to 1 over C, which is greater than or equal to 1 over B. Okay, so these are just like the three tools in our toolbox. Among the tools in our toolbox we'll be using. Groovy? All right, so here, basically, let's just sort of compare these. So would you agree, first of all, that the triangle that's written on the right that has a height of tangent theta, would you agree that that encloses the largest area of the smaller triangle, which is similar, and the sector? Good. So basically, the area of the largest triangle is the largest area. The area of that sector is the middle area, and the area of the smaller triangle there is the smallest area. Good so far? So now let's just kind of match up what we've got going on. So this guy here has a length of what? We're on the unit circle here. We're on the unit circle. So we basically have, this ordered pair is the ordered pair cosine theta, sine theta, all right? And then this ordered pair right here is what? Beautiful. 1, 0. Good so far? Now, where else are these lengths used? So that you see that this is going to be a length of 1. And isn't this one as well? And this one too? Okay. So that's going to serve for all of our triangles. Now the big triangle is this guy here. Whoops. With that yellow base. Good so far? And so basically what's happening is we're using, you might be a little mystified about this ordered pair being 1 comma tangent theta at this line right here. Do you see that it's going to have the same slope as this hypotenuse here, right, for that smaller triangle? So now what happens is, you know, the slope is the change in y over the change in x, right? So the slope of this is going to be, good, tangent theta, because our angle is called theta in this case, right? So if you looked at our slope and you said, oh, the slope is the change in y over the change in x, which is going to be sine theta minus 0, because we have an ordered pair at the origin, right, at 0, 0. Right? And we have 2 ordered pairs. For this guy, we have cosine theta, comma sine theta, and 0, 0, right? So that'll be over cosine theta minus 0, which is sine theta over cosine theta, which is tangent theta. So we have a slope of tangent theta, right? So if you just take a look here, if you go tangent theta up, right? And if you're making a slope triangle here, and you go tangent theta up, which is here, tangent theta is the same as tangent theta over 1, right? So if you go tangent theta up, you got to go 1 to the right. So that's where we get the ordered pair 1 comma tangent theta, just using slope, all right? So coming over to this guy, the area of this triangle, right, so we'll just call it area 1, I guess, is equal to 1/2 times the base, which is 1, times the height, which is tangent theta, right? So area 1 is tangent theta over 2. Area 2, we're using the area of a sector formula, and so we'll get 1/2 times theta squared, and what's our radius? 1/2 theta r squared, right? So we'll have 1 squared. So area 2 is going to be theta over 2. And then area 3, this little triangle, 1/2 times base times height. Area 3 is going to be 1/2 times 1. And what's the height of this guy? Do you see it's the sine theta? So area 3 is going to be sine theta over 2. Now you might wonder why the heck are we going on about this, right? Basically, we're looking at showing, we want to show that this limit as x approaches 0 of sine of x over x has an output of 1, okay? So basically, we want that sine function, right, to be in the middle, right, in the middle. So let's work it, okay? We're going to use a mixture of identities and some trickery, and we're going to do this. And instead of x's, we're going to have thetas, all right? So here we go. Coming down here, would you agree, first of all, that area 1 is greater than or equal to area 2, which is greater than or equal to area 3? Good. So what does that give us? Tangent theta over 2 has to be greater than or equal to theta over 2, which has to be greater than or equal to sine theta over 2. But, you know, we want sine theta in the middle, and we don't want it to be over 2. So if we multiply, right, everything by 2 over sine theta, right, in the inequality, and then we'll have, you know, what we had before. Oops, my bad. This would be still theta over 2, and this would be tangent theta over 2. And then let's simplify this, okay? So what's going to happen here, you know, you can see, I'm sure that all the 2's will divide out, right, to be 1. And then, you know, tangent theta is sine theta over cosine theta, and that's being multiplied by the reciprocal. You'd have 1 over sine theta, right, is greater than or equal to theta over sine theta, which is greater than or equal to, good, this divides out to be 1, doesn't it? Okay, so coming back, these sine thetas divide out, you know, and by the way, I did a little different order. Tangent theta is equivalent to sine theta over cosine theta, and then I multiplied by the reciprocal. All right, so we're going to end up here with 1 over cosine theta is greater than or equal to theta over sine theta, which is greater than or equal to 1. But using this guy here, right, this relationship here, because remember, we want sine theta on top and theta on the bottom. So sine theta in the numerator and theta in the denominator. So we're going to use that fact that the reciprocal is going, if we use reciprocals, we have to flip the inequalities. So this is going to be cosine theta over 1, which is cosine theta, would be less than or equal to sine theta over theta, which in turn is less than or equal to 1. So now, this is the beauty of it, right? So let's do some side work. The limit as theta approaches 0 of cosine theta is what? Good. Cosine 0 by direct sub. Sorry. Cosine 0 by direct substitution, which is 1. Right? And on the right side, the limit as theta approaches 0 of 1 is 1. Beautiful. Now the other one, the limit as theta approaches 0 of sine theta over theta is by direct sub sine 0 over 0, right? Which is 0 over 0, which is indeterminate. But by the squeeze theorem, right, since these expressions are all right next to each other, right? They're all very close, these areas, right? So by the squeeze theorem, it turns out that the limit as theta approaches 0, sine theta over 0, sine theta over theta has to be 1, right? So let's just check this out. Let's write it in, okay? So if we apply these limits, this also has to be true. And what did we get for these things? We got a result of 1. So that has to be less than or equal to the limit as theta approaches 0 of sine theta over theta, which has to be less than or equal to that other limit, which is also 1. So, at the end of the day, by the squeeze theorem, the limit as theta approaches 0 of sine theta over theta has to also be equal to 1. Isn't that awesome? I love that one, using the different areas. Okay, so, you know, you're not going to have to, use all of this, right? I just wanted to show you an example of the squeeze theorem and tie it into these special trig formulas. You have to, basically, you have to memorize all of this stuff, right? So you have to memorize these special trig limits. You're going to use them not only here, but in Calc 2 and Calc 3, all right? So you might as well get them in your brain. All right, so here we go. Now, again, we're going to work with some trig stuff. Using trig identities is another way to analytically evaluate a limit if it gets an indeterminate result. So we're going to look at that. We're also going to be looking at different strategies, all right, where we have to rationalize the numerator and all that good stuff. So why don't you guys try this example here, pause the movie, try this example, and then work along with me and see how you did, all right? Okay, let's see how it went. All right, so by direct substitution, right, what do we get here? Good, we get tangent at 0 squared over 0. So wherever, oops, that's weird. It's kind of cool. I didn't mean to do that. Okay. So wherever we had an x, we plugged in a 0. And then what do we get for that? Good, tangent 0 is 0. God, my leftiness is coming out, guys. Okay, tangent 0 is 0, so we'd get 0 squared, which is 0 over 0, and that means indeterminate, more work, right? Okay, so let's do it. Well, we don't have a whole lot of algebra we can use at this point, but we do have trig, right? Okay, so let's see what we have here. Recall that tangent at x, so I'm initially writing it like this. So the limit as x approaches 0 of tangent at x, the quantity squared, over x. This will give me the limit as x approaches 0 of sine at x over cosine at x over x. And that sine at x over cosine at x is squared using the quotient identity for tangent at x. With me so far? Awesome. So this guy will be the limit as x approaches 0 of sine at x squared over cosine at x squared. And I'm going to just write that times 1 over x. I'm multiplying by the reciprocal, right? Now, do you remember that we've got that special trig limit, right, that we just learned that involved the sine at x? So basically, this is what we're going to do. We're going to use some trickery and say that we get the limit as x approaches 0 of. We're going to use one of the factors of sine at x And then we're going to put that with that x, right? And then we still have another factor of sine at x that we need to use, and that's over cosine at x squared. Cool so far? Awesome. So now, remember the limit of a product is the product of the limits. So we can split it and say the limit is x approaches 0 of sine at x over x times the limit as x approaches 0 of sine at x over cosine at x squared. So let's see what we get. We'll get, for two different reasons, okay? Using a special trig limit, we're going to get 1 for this guy. So this whole limit is 1, okay, and that's from special trig limit. And then times sine at 0 over cosine at 0. Sorry, that's a 0, not theta. Sine at 0 over cosine at 0, the quantity squared. And this is by direct substitution, direct sub. So then we'll get 1 times 0 over 1 squared, which is just 0, but you're getting it for the right reason. Okay? Awesome. All right, so here we go. Let's see how you did with this guy. All right? So now, there's a couple ways a person could go about a problem like this. You could use Pythagorean conjugate. You could use change everything in terms of sines and cosines. I think I'm going to opt to do that. But first, let's see what we get when we use direct substitution. We'll get 1 minus tangent at pi over 4 divided by sine at pi over 4 minus cosine at pi over 4. Right? And from there, do you see, you'll get 1 minus 1 over root 2 over 2 minus root 2 over 2, which is 0 over 0, which means you got it, more work. So, coming over here, we'll do the limit as x approaches pi over 4 of 1 minus sine at x over cosine at x divided by sine at x minus cosine at x. So all I did, again, is I used the quotient identity for tangent at x to change it to this. All right, so in turn, let's get a common denominator for this expression in the numerator. So we're going to end up with the limit as x approaches pi over 4 of 1 is the same as cosine at x over cosine at x minus sine at x over cosine at x over sine at x minus cosine at x. So all I did here is I rewrote 1 as cosine at x over cosine at x, so I could get one happy trig expression in the numerator. So now this will give me the limit as x approaches pi over 4 of cosine at x minus sine at x divided by cosine at x, and I'm going to multiply that expression in the, I'm going to multiply by 1 over sine, or multiply this expression by 1 over sine at x minus cosine at x. Now, do you guys see that these terms here are opposites right here? So when you divide them out, you'll get -1. Now, if you forgot about all that, you can factor out a -1, right? So you can say, okay, we'll get the limit as x approaches pi over 4 of negative sine at x minus cosine at x over cosine at x times 1 over sine at x minus cosine at x. So this guy can be written like this. And of course, we can divide this out. And we'll end up with the limit as x approaches pi over 4 of -1 over cosine at x. Good so far? So now finally, using direct sub, well, almost finally, we will get -1 over cosine at pi over 4, right? Which will be equal to -1 over root 2 over 2, which is -2 over root 2, which happens to be negative root 2. Cool? All right. So, and again, graphically, you can verify all of these things graphically. All right. All right. So there is, different strategies. Oops. Okay, that was weird. Okay, so strategies for finding limits. Always, always, always try using direct substitution first. If it works, you're good, right? You go to step 2, or if it works, you're good, you're done. If it doesn't, you got to go to this next step. So if you obtain an indeterminate result when using direct substitution, remember, 0 over 0, try factoring the numerator and denominator, dividing out common factors, and then use direct substitution on the new expression. This is the one that functions that agree in all but one point. Now, you could also try to rationalize the numerator, like we did in the warm-up problem, and then use direct substitution on the new expression. If you obtain an indeterminate, I've been saying indeterminate, sorry. I can fix it here. Indeterminate result when using direct substitution on a trigonometric expression. You can try rewriting using trig identities, which is what we did in that last problem. You can, and then use direct sub. You can rewrite the expression using trig identities and use the special trig limits, the limit as x approaches 0 of sine at x over x is 1. The other one is the limit as x approaches 0 of 1 minus cosine at x over x is equal to 0, right? And sometimes you're using a combination, right, of everything. And then also verify your result by using the graphing feature on your graphing calculator. Okay, so here we go, example 10. Direct substitution, right? I'm just going to go a little quicker here. Do you see if I plug in a 4, I end up with root 2 minus 2 over 4 minus 4, which is 0 over 0, which means more work, indeterminate, right? I'll write an indeterminate since I've been spelling it wrong the whole time. My bad. All right, so here, the skill for that was, good, rationalize the numerator. So we'll have root x minus 2 plus 2, and then you balance it out by multiplying that denominator by the same thing. And let's see what happens. Can we take off our limit notation? No, good, because we're not ready to use direct substitution yet. So this is going to give us root x minus 2 squared minus 2 squared over x minus 4 times root x minus 2 plus 2. And remember that trick, don't multiply out the denominator. If you did things right, that x minus 4 will divide out. So we'll get the limit as x approaches 4 of x minus 2 minus 4. Oh, gosh. My bad, guys. As I'm saying that, I'm like, okay, I forgot my root 2. Do you see that? Hang on. I'm going to go back here. I forgot that root 2. This should be all root 2's, right? Because of that root 2 in the problem. So then this, of course, instead of, it would be, you know, root 4. No, it would be, well, root 4 is correct, but it would just be x minus 2 all over x minus 4 times root x minus 2 plus root 2. And we have x minus 4 in the numerator now over quantity x minus 4 times quantity root x minus 2 plus root 2. And the x minus 4's divide out. No, x minus 4's divide out. And we'll be left with the limit as x approaches 4 of 1 over root x minus 2 plus root 2. Using direct sub, we will have 1 over root 4 minus 2 plus root 2, which gives us 1 over 2 root 2's. You see that? And you're done. Woohoo! Okay, guys, we're almost done. How many more problems did I torture you guys? Give you guys. We've got 4 more, okay? So do your best on these. Why don't you go ahead and pause the movie, see if you guys can do these ones, and then come back when you're ready, and then I'll work them out with you. Alrighty, let's see how you guys did. Again, quickly, direct substitution. Be careful. Delta x is approaching 0, not x. So we'll end up with 2x squared minus 2x squared over 0. So we get 0 over 0, which is indeterminate, more work, right? Well, more work on this problem means good, algebra. So it's up to you how you want to work this. You could either multiply everything out, crunch it out. If you factor out a 2, you'll have the difference of squares, right? So remember that you can bring a constant out of the limit. So you can write it like this: 2 times the limit as delta x approaches 0 of x plus delta x squared minus x squared, which is a difference of 2 squares, over delta x. This is going to give us 2 times the limit as delta x approaches 0 of. Now our first quantity being squared is x plus delta x, and then we'll have minus x, And then the next one would be x plus delta x plus x. Good so far? And that's all over, whoops. And that's all over delta x. Now, we'll get 2 times the limit as delta x approaches 0 of, do you see the x's 0 out in this guy? It'd be x minus x, and then we'll have a delta x. So we get delta x times 2 x's plus delta x all over delta x. So the delta x's divide out to be 1. So we'll get 2, and then this is using direct sub, 2 times 2x plus 0. So in for delta x, I put 0. And we get 4x, and we're all done. How'd you do? Awesome! I knew you could do it. All right. So now with this guy, let's see what we get. Again, direct sub. Let's see. We get 1 over negative 3 plus 1/3 is 0 over 0. So that means indeterminate, more work. So the more work in this one again will be great algebra. All right. Well, with this one, you know, why don't we simplify the rational expression, which basically means getting one happy fraction. So let's see how we're doing. This will be the limit as x approaches 0 of. Do you guys see that the common denominator in the numerator is 3 times x minus 3? And the first one is missing. Good. The 3. And then the other numerator is missing. Perfect. X minus 3. All right. And then this is over x. So this in turn will be the limit as x approaches 0 of 3 plus x minus 3 over 3 times x minus 3. And then again, I'm going to multiply by the reciprocal. So this is the numerator. And so I just wrote that one. And we're going to multiply times 1 over x. So we will get the limit as x approaches 0 of x over 3 times x minus 3 times 1 over x. And that's fortunate. Those problem children divide right out. And finally, I'll write one more step to make it pretty. This simplified rational expression looks like this. And now we can apply direct sub. And we'll get 1 over 3 times 0 minus 3. So n for x, I put 0. And we have, dun, 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 negative 1/9. How'd you do on that guy? Great. Okay. So this one, theta's going to 0. Using direct substitution, we would have cosine 0 times tangent 0 over 0, which is good. This would be 1, this would be 0, so 1 times 0 is 0 over 0. And that means, of course, more work, indeterminate. So, coming back over here, we'll get the limit as theta approaches 0 of. Well, cosine theta we can't do much with. Tangent theta we could write as sine theta over cosine theta using the quotient identity. and that's all over theta. So again, this guy is equivalent to this factor. And you see that the cosine thetas divide out to be 1. And we end up with the limit as theta approaches 0 of sine at theta over theta. But what is that? Good. That is 1. And that's by the special trig limit. Not by direct sub. It's the special trig limit. Okay, so basically this whole thing by the special trig limit is 1. Cool? All right. And we're done. Woohoo! That was a long one, all right? Hang in there. You know, calculus isn't supposed to be easy or fast, but you're going to get better with all your skills as you go on and, you know, finish off whatever math you need. All right? So have a fabulous day. Bye.